So there will be often times where the integrals are set up this way, and sometimes you can see here that solving for the integral can be really difficult. So for example, here we have that we want to integrate the inner function, which is in terms of y. But if you try to find the antiderivative of e to the y cubed, that one you cannot do. You can't. There's no integration technique that will allow you to integrate e to the y cubed. So sometimes reversing the order of integration can help out. So in order for us to do that, we first have to figure out what the region should be. So we're going to take this piece of information, so this inner integral, right, to try to figure out what exactly is happening. So here you can see that your y values are going from y equals x squared to y equals 9. And then you can see that my x values, which is the outside part, goes from x equals 0 all the way to x equals 3. So what we're going to try to do is attempt to draw the region. Okay, so we're going to start off by looking at the first part, y equals x squared. So y equals x squared is a parabola. It looks like that. And it looks like it's cutting through the parabola, y equals x squared, and going all the way to y equals 9. So y equals 9 is right there. So it looks like this is going to be the region that we were looking at, because this one seems pretty standard, and you can see that the x values go from 0 all the way to 3, right? And that would be correct, right? Because if I were to take 3, plug it into the parabola x squared, you would get a 9. So this seems like the region that we are basically looking at. And the region that was enforced here is going in the upward direction. Okay, so here was y equals x squared, and here's y equals 9. So now what we're going to do is we're going to try to reverse the limits of integration. So we're going to have a double integral. My graph, or my multivariable function, is going to be the same, but now I'm going to want to have it in terms of dx and dy. So notice that here there's a difference. Instead of having the dy dx, we're going to swap it with dx dy. So just swap the limits. So in that case, because x goes first, we're going to draw an arrow going left and right. Notice that the first thing that it's going to cut is through x equals 0. That's the first one. And the last one is going to cut is x equals whatever this graph is. So because it's at y equals x squared, let's go ahead and rewrite that in terms of y equals, so square root both sides. X is equal to plus or minus square root of y. Alright, now in this case, it would make sense for it to be the positive one, because we know that your x values are increasing, so this will be the square root of y. From 0 all the way to the square root of y. Now what about my y values? Well, now we're going to look at what are my y values in this case. Alright, so you can see this guy's just going to go from 0 to 9. And this will be my solution. So you can see now that not only did I switch it, but now I have this dx. I can now go ahead and integrate the x out first and hope that that will help make this integration of e to the y cubed much better after I do the first integration. So let's do this next example. So we have the integral from 0 to 8, and integral from cubed root of y to 2 of the square root of x to the 4th plus 1 dx dy. So you can see here the integral of the first one with respect to x is a lot complicated. You can't do this. You can try using trig sub, which would be a huge mess. So let's go ahead and draw the region one more time. So you can see here these are for x's. So we got x equals cubed root of y, and it's going all the way to x equals 2. And then the outside is going from y equals 0 to y equals 8. All right. So now let's go ahead and draw this. So x equals x cubed root of y, that can be a little difficult to kind of think about. So maybe one thing that you can do is rewrite this in terms of x, in terms of y equals x. So I can cube both sides and I get y equals x cubed. So this graph actually, okay, so you kind of think about it this way. This guy is basically x equals cubed root of y. Okay, I just made it a little nicer made it in terms of x, so that it's a lot easier to work with. All right, and then you know that it's going from there all the way to x equals 2. Okay, so x equals 2. All right, so now remember, this is where it starts and it ends at x equals 2. So it looks something like this. So this is the region right here. Okay, and you can see that the y values go from 0 all the way up to 8. All right, now you have to be very careful because sometimes it can be really easy to be like, oh, this top one is the region. But no, the region is this guy. Because this would make sense when I put the arrow. Since I'm doing the arrow in terms of the x values, notice that it's cutting through this x cubed graph and coming out of x equals 2. Okay, so this one would make a lot more sense. All right, so now let's go ahead and rewrite this. So we want to go from the bottom up. So this will be double integral. So square root of x to the 4th plus 1 dx dy. So notice, oops, that's wrong. Because I want to go ahead and make it dy dx. So change up the limits of integration from this guy to this guy. So now you can see that the y, okay, so I have an arrow pointing up, so it's cutting through 0 all the way up to y equals x cubed. So 0 all the way to x cubed. And now my x values, you can see them here, it's from 0 all the way to 2. So this will be my solution. Okay, you can see now that maybe this is going to be a lot easier to work with because the integral of this with y, you will have a y. Plug in the x cubed, you can see that you can do a u sub, which is going to be a lot easier to work with. All right, now finally, let's go ahead and do this last problem because this is going to be a really good setup for our next section, which is going to be polar coordinates. So we want to set up the double integral that represents the volume of the region that is enclosed by the graphs z equals 16 minus x squared minus y squared and z equals 3x squared plus 3y squared. All right, so what exactly is happening here? So this is a really good example because we haven't really quite done something like this. Especially when it comes to where these guys are intersecting at. So let's go ahead and graph this. So I'll go ahead and do this. So you can see that this first guy is just a paraboloid, elliptic paraboloid. So it's going up to 16 and it's going downward. Something that looks like that. And you got this other guy, which is z equals 3x squared plus 3y squared. Notice that there's no increase. This is a happy paraboloid. This one was sad because you got negatives here. This is going to be a happy one because they're both positive and they start at the origin. Okay, so let's go ahead and do that. So it starts at the origin and it's just going to be going upward. So you can see that there's going to be a point where these guys are going to intersect, but they're not just going to intersect at a point. They're going to intersect at a particular region. So what we need to figure out is what is this region where they're both intersecting? So what is the region where both paraboloids intersect? Okay, and notice that this region is going to be a function of x and y. So if we can figure out what that region would be, we can easily figure out what exactly that's going to, what exactly, how we can integrate this. So how can we figure out what this region is going to be? And then that way, when we figure out this region, we can place it on the x and y plane. So this intersection, right, is going to be wherever the z values are going to meet, wherever these two equations are going to be equal to each other. So just how we did it before, that's what we're going to do here. So we're going to have 16 minus x squared minus y squared is going to be equal to 3x squared plus 3y squared. So let me go ahead and add x squared and y squared to the other side. So you get 16 is equal to 4x squared plus 4y squared. Notice that I can divide by a 4. And you get that 4 is equal to x squared plus y squared. Alright. So what exactly is this? Notice that here I didn't get a points. Just like how we've been looking at the other guys, we haven't been getting any points. This time I got an equation. So this tells you the region in which you need to go ahead and integrate. So this is a region, so the biggest region that I'm going to get is a circle of radius 4. Radius 2 in this case. So that's going to be this region right here. This guy. Alright, so this is going to be my region that I'm going to have to integrate. So you can see that this is going to be the one that I'm going to be looking at. So imagine that you're just looking at this particular circle. This circle is kind of like on the x and y plane. Alright, so now let's go ahead and use this region to try to figure out what my integration should be. Okay, so now what we're going to do, let's go ahead and set our double integral. And let me do this instead. There we go. Okay, so double integral. Now, what's going to be inside of the integral in the integrand? Well, if you were to think about the x and y integration, and I had a graph on top and another graph on the bottom, then remember there will be the upper minus the lower, right? So you'll have the upper minus the lower graph. So it'll be f of x minus g of x. And you will just take the integral. There's really the same thing. It's going to be exactly the same thing here. So think about which one's going to be the top and the lower one. You can see that the top is going to be the black paraboloid, which is a 16 minus x squared minus y squared, minus the bottom paraboloid, which is going to be the green one, which is a 3x squared plus 3y squared. Okay, so still the upper minus the lower. Still same thing. All right, so now all we really got to do is let's go ahead and figure this out to find the limits of integration. So notice that I'm going to just use case 1 for no apparent reason. So, and I'm going to try to solve for y. So notice that this guy, when I solve for it, you're going to get y squared equals 4 minus x squared. Take the square root, plus or minus. Y equals plus or minus square root of 4 minus x squared. So this bottom part of the circle is the negative part, negative square root of 4 minus x squared. And this top part is going to be the positive version, so this positive 4 minus x squared. So you can see by this arrow, it's going to be going through negative square root of 4 minus x squared and going to come out through 4 square root of 4 minus x squared. And this is in terms of dy. And my dx is just going to be the x values where the circle is at. So from negative 2 all the way to 2. Since we're only setting it up, this will be my answer. And actually, solving this would be horrific because you have these crazy square roots that may or may not integrate when you plug them in. So that can provide a challenge. So that's why we have other different types of coordinate systems that can help us figure this out. And you'll see that polar coordinates actually is a way better way to kind of do problems of this kind. So that's something that we're going to be covering very soon. So that's a little bit of double integrations with iterated integrals, okay, over some general regions.